Given particular information, we can come up with the equation of a conic section, and that's what we're asked to do here. We're told it's a parabola, and the directrix is x equals -3. Because it's a parabola, we know that the eccentricity E is equal to 1. I find it useful to orient myself by drawing basically whatever information we have. And here on the xy plane, the information that we have is that the directrix has an equation x equals -3. So I know it's a vertical line to the left of the y-axis. And that tells me two things. But before I get to what it tells me, let's remind ourselves that the equation of a conic section in polar coordinates is r is equal to ED divided by 1 plus or minus either the sine of theta or the cosine of theta. Now the two things that I can get out of knowing that the directrix has an equation x equals -3 is, r, that we have a cosine situation here because this would be a horizontally oriented conic section. And because the directrix has an equation x equals -3, I know that we have a subtraction in the denominator. Putting this together, we have that r is equal to ED is going to be 3 divided by 1 minus the cosine of theta. That's our equation. Let's do that one more time with some different information. We're going to be looking at an ellipse with an eccentricity of 0.6 and a directrix that has an equation r is equal to 4 times the cosecant of theta. Well, we know that E is 0.6, and let's look at this directrix equation. If we convert this to rectangular coordinates, then we'll know what it looks like, right? So we're going to multiply both sides by the sine of theta. We get r times the sine of theta is equal to 4. So the equation of this directrix is y equals 4. Again, that gives me some information that I'm going to represent visually. Here are my x and y axes. And I have a directrix that is horizontally oriented 4 units up. Since that's my directrix, I again know two things. R is equal to ED divided by 1 plus or minus either the sine of theta or not a fraction, or the cosine of theta. And with this particular directrix, it's horizontal, so I know that my ellipse is vertically oriented. That means we are looking at a sine function, and because the directrix has an equation y equals +4, this is going to be a plus in the denominator. E is equal to 0.6, y is equal to 4, and y is equal to d. So ED is equal to 0.6 times 4. I'm going to go with representing this as a fraction, and so we have 12/5 for ED. Then r is equal to 12/5 divided by 1 plus e times the sine of theta, and again I'm going to go with a fraction for e, 3/5 times the sine of theta. Now that I have fractions both with a denominator of 5, it makes it a little bit easy to simplify the complex fraction, and we end up with r is equal to 12 divided by 5 plus 3 times the sine of theta. Next, we're going to go the other way around and graph from an equation. Sketch the graph of r equals 1 over 2 plus sine of theta. I'm going to rewrite the equation just so I can work with it. R equals 1 over 2 plus the sine of theta. And remember that the first thing we want is we want to turn the the constant term in the denominator to a 1. I'm going to achieve that by multiplying numerator and denominator by 1/2. When I do that, I get r is equal to 1/2 divided by 1 plus 1/2 times the sine of theta. Now I start reading the information from the equation. Because I have a coefficient of 1/2 in front of the sine of theta after turning the first term in the denominator into 1, I know that e is equal to 1/2. From the numerator, I can see that ED is equal to 1/2 because that's what I have in the numerator. That represents ED. Since E is 1/2, I know that D must be 1. Now, since E is 1/2, I know we're looking at an ellipse because E is less than 1. Because it's a sine in the denominator, I know we are looking at a vertically oriented ellipse. And because d is a positive number, I know that the directrix is a horizontal line above the y-axis. Let's put this together on a polar grid. As you may recall, our conic section is going to have its one focus at the pole. That was the setup when we developed the equations. The directrix is y equals 1. And I'm going to go ahead and make the third circle out have a value of a radius of 1. And now I want to plot some points. I'm going to use a theta r table, and remember that our equation was r is equal to 1 over 2 plus the sine of theta. Values I want to pick for theta are quadrantal angles, and so 0, pi over 2, 3 pi over 2. Nope, I always skip pi, don't I? Pi and 3 pi over 2. When theta is 0, I have sine is 0, and so r equals 1/2. When theta is pi over 2, in the denominator I have 2 plus 1, and so I have a value of 1/3 for the radius. When theta is equal to pi, again, sine of theta is 0, and so the radius is 1/2. And when theta is equal to 3 pi over 2 in the denominator, I have a negative 1 in place of sine, and so 1 over 2 plus sine theta becomes 1. Plotting these on the polar grid will give me an idea of what this looks like. So at pi over 2, the radius is 1/3, so I'm on the first ring out. At 0 and pi, I'm at 1.5 rings out because my scale is 3 rings is equal to 1, like the radius of 1. And so I, for 3 pi over 2, should be on the third circle out there. Now, folks, this is going to present a challenge for a lot of people. I see them drawing things that look very asymmetrical. This is supposed to be an ellipse after all. And so if your drawing looks kind of like an upside down teardrop, I really want you to make a better effort than that. One of the ways that you can do that is to take advantage of symmetry. I see that we have a vertex here on the line theta equals pi over 2. And 1/3 of a unit from that, I have a focus. If we look at the vertex at the on the line theta equals 3 pi over 2, 1/3 of a unit from that will give me another focus. In this case, we have from the origin at the, well, on the polar axis, we're at 1.5 units from the pole, right? Left and right. Those are points on the ellipse. Therefore, if I draw vertical lines that go through known points on the ellipse, then I know that the line segment, or the line that goes through the focus that's on the line theta equals pi over 2 will intersect these vertical lines due to the symmetry of the ellipse. And so that gives me kind of a little indication as to where I can put a couple of more points. I can always put more angles into the equation, but at this point, I think I'm ready to draw something that should be reasonably accurate for this particular ellipse. So connecting the dots that I have, trying to make it curvy and smooth, that's the equation of my ellipse, or that's the graph of my ellipse. We can identify a few pieces of information here, and I'm going to do that. We have vertices, as we can see, at 1/3 pi over 2 and at 1/3 pi over 2. We can also identify the center. The center is going to be, well, it's on the y-axis. And the y-coordinate is going to be the average of the values of the vertices. And the y values of the vertices are 1/3 and -1. Right now I'm switching to rectangular coordinates because these numbers are easier for me to deal with right now. The center then is going to have a y-coordinate that is an average of these two. So 1/3 - 1 over 2. and we'll see that that is negative 1/3. That agrees with the picture that we have, because at r value of negative 1, or at an r value of 1/3, excuse me, I'm halfway between the two foci, I'm halfway between the two vertices. In polar coordinates, this is going to have an address of 1/3, 3 pi over 2 for the center. You know what? I just realized I had bad form here. Oh my gosh. I've marked that the directrix is the line y equals 1, and that's on the third circle out, but I haven't actually marked the scale on the polar grid. And really, to communicate properly with anybody who wants to read this, I should. So I'm marking on the polar axis. The third circle out has a radius of 1, and that's going to be good enough to communicate to my audience, you, what this scale represents.